Hi everyone, welcome back to another one of our screencasts to show you some inner workings of the ECL. I'm Vaseem, Solutions Application Developer from Align Bio.
I'm Erica, and we're going to walk through the Golden Gate assembly script. This includes Golden Gate reaction itself, PCR, and then running it on a gel. And as part of this sort of walkthrough, we'll go through the script, which is also on GitHub. We'll also talk about some of the challenges, small volumes,
Yes.
a primary challenge, and we'll also walk through this tool that's part of Command Center called Command Builder. That's like a really easy way, especially if you're like new to programming in this language, to like set options and even see what options you could configure in a given command.
That
So,
is true.
take it away.
All right, let's dive into it. So shown here, like before we actually dive into the code, I want to show you what the overall overview of this whole experiment is. So we are starting off with our samples, the G blocks that we have, diluted them in water, and then we're using the different components of Golden Gate assembly, T4 ligase, BSA1, and buffer, etc. We are putting them in our PCR plate, incubating it according to the number of fragments you have. It totally depends on the experiment that you're trying to perform. After you do that, you're actually going to add PCR mix and primers directly onto the reaction. We're going to talk about a little bit on this when I come to the code, but this is an important point where we add the PCR directly to the reaction itself and not the other way around. We are taking a sample from the reaction and then preparing a PCR reaction from that. And in the end, after the PCR reaction is complete, we are taking a part of the PCR reaction and then performing gel electrophoresis to QC or make sure that the final product has the right size that we're expecting.
And one other note, so probably most people are familiar with Golden Gate as a cloning technique for plasmids. And so we're repurposing this and using it in a slightly different context. So normally you would take like a backbone and insert an insert, transform it into bacteria, and then like pick colonies, right?
Right.
And we're doing something slightly different, which is we take a one G block, pop in another G block with Golden Gate,
Yeah.
and then we PCR that insert using the primers. And so the PCR becomes the way for us to identify successful Golden Gate products rather than a transformation and a plating. So
That's true.
that's just a note different than how most
Right.
folks probably have usually used Golden Gate.
So as a next step, I want to add a little bit on top of that. Like once we have that linear product, we can actually use cell-free expression to express the construct we have within that assembled DNA. Okay, diving into the code. So here I'm just giving it what samples we are using. The first one is one of the G blocks. The second is the other G block. I'm also giving it the what molecules the G blocks are composed of. We talked a little bit about this in our previous screencast about what an identity model is, what a fulfillment model is, and what the actual sample is. The reason I'm giving it is so that I can identify the molecular weight, etc., just for our purposes here, and the concentration. And what I'm doing in this step is trying to set up a four reaction plate where I'm adding 3 microliters each of each G block into the first well, 4 into second, 5 into third, and then 6 into the fourth one. And to these, I'm going to add the T4 DNA ligase, the ligase buffer, and then BSA1 enzyme.
And so, but tell us more. So you have this whole different number. You have this range of sizes of reaction volumes you're testing. Why'd you do that?
So previously, we had an issue when I was trying to add just 2 microliters each of each G blocks. So instead, I was going to try in this particular script to increase the volumes of each G blocks so as to not get any unsuccessful transfer from the source G blocks. Because through our course of optimization, we have noticed that Emerald sometimes can be not very reliable if you're working with very small volumes, especially if it's less than 3 microliters. And
Yeah. So,
hence,
this is in fact a super common issue in automation, Emerald and any other automation. It's like small volumes are tough to pipette reliably, but it's worth putting a flag on this that like um kind of fiddling around with like what the reaction volume of this experiment was such a big deal that it literally appears in the final code as like a series of options that are being tested out. So
Right.
just worth really putting a flag on. Small volumes are tough and need to be optimized.
Right. Yeah. One more thing I want to mention is like previously I was using a 20 microliter of total reaction. Instead, I have upped that volume to 30 microliter in this case to make sure that there was enough volume of each component that I'm adding to the reaction.
Hmm.
Hopefully that makes sense. As you can see, I'm adding at least 3 microliters of each reagent here instead of 2 microliters, so as to make sure that things are transferred correctly into the well that we are trying to mix in. Again, here's another setup code where I'm trying to just see what fragments and how much volume of each different component is being added to the reaction. Here I just plotted the table for visual purposes. And finally, I'm just accumulating all the volumes of different components into these individual lists so I can then directly give it to the command following that I'm going to show you in a second.
Right. So everything above this point is just sort of setting up, defining what is the sample ID of the ligase buffer, defining like arrays essentially that contain the different volumes that are going to be necessary for all the different components. And then below is where the pipetting will begin.
Right.
Yeah.
So yeah, finally we are here to the point where we're actually going to pipette everything into the different wells. So instead of doing everything in like one transfer command, I'm using like 4 different commands to set up 4 different reactions for simplicity purposes. And for transfer commands, we're going to specify from where we are going to transfer. And as you can see, I have specified this variable reaction components that I had set up earlier, which is composing of the G blocks, ligase buffer, BSA1, and nuclease-free water. And then I'm transferring from those sources into this B2 well on a plate that I defined in my label container operation. And then I'm labeling this reaction itself to Golden Gate reaction 1, so I can reference this later down the code. So you don't have to like remember this particular reaction is present in B2 well on this particular plate. So you can directly reference it by the name. And I'm also specifying once the experiment is complete, where should this sample be stored? So I'm specifying it should be stored in a refrigerator. Similarly, I am specifying the rest of the 4 reactions in well B3, B4, and B5 respectively.
And tell me more about why did you have to choose? You've named wells of a 96 well plate individually. Did you have to do that? Was there a way for the sort of software to automatically map which wells you were going to use for you, or why'd you choose to select your own wells?
So the reason I'm trying to select my own wells is first to avoid any edge wells, because like if you're going to not specify anything, just specify the plate, I think the default value is going to use well A1 if it's available. And that's kind of pretty close to the edge of the well, and whenever somebody's trying to put like a lid onto the plate and remove the lid onto the plate, there might be a case where the sample could be disturbed, or it could also evaporate. There are chances of it getting evaporated. So it's better to use
Yeah,
a well that isn't like somewhat in the middle of the plate.
yeah, edge effects are real and to be avoided,
Yes.
for sure.
Yes. And the reason I'm trying to label everything is so I can like just reference them later in my code itself. So I don't have to, again, give it the well and plate number.
Hmm.
As you can see in this mix operation, I'm just directly giving it the reaction name. So it knows which well is it present in, so it can then go mix it using a pipette method. And it's going to use like a 15 microliter mix volume to mix it with the pipette up and down 10 times, as I've specified here. So once I run this command, I'm going to get out this protocol object, which is going to perform this operation. So that is just mixing the components together in a plate and then keeping the plate once it's done. So once that protocol is completed, I'm then taking that protocol variable itself, because I named it here. And then I'm taking the container out. So I'm going to basically take what plate it is actually outputting out of the reaction, and then using that plate in my next protocol, where I'm basically incubating that plate on a thermocycler based on the temperature profile that is suggested for two inserts for the Golden Gate reaction itself. 16 minutes at 37 degrees followed by 5 minutes at 60 Celsius.
Cool.
Then I'm waiting for 30 minutes for this reaction to cool down. And then I'm centrifuging this plate again at a low intensity for 2 minutes just to make sure that all the liquid is sedimented at the bottom and not on the side of the well.
Mm-hmm.
Following this protocol,
Out of curiosity, does it get centrifuged before it gets incubated also, or just after? Just like
it's after. So
like
these
spin it down?
operations are performed in order. So after incubation is you got to wait for 30 minutes and then the centrifugation is performed.
Mm-hmm. Okay.
Yeah. Again, you get the protocol object for you to track. Then here comes the important part that I mentioned where we are adding the PCR components directly onto our reaction instead of taking a bit of our reaction and then performing PCR reaction on that sample. So the reason for it is like, since the reaction itself is 30 microliters in total volume, trying to pipe it out like 5 or 10 microliters from this volume might be, we have noticed that it has been unreliable in past for us. So instead of doing that, what I'm doing is like I'm just adding my PCR mix and primers directly onto our reaction and then performing the PCR reaction itself on the same plate. So I'm just seeing what samples are output from the Golden Gate prep protocol. So these are the samples, means these are the 4 reactions that we have prepared on our Golden Gate plate.
Mm-hmm.
Then I'm assigning it to the samples input for the PCR. And then here I'm specifying what primers I'm going to use. This is going to be dependent on your use case and your constructs itself. And
these primers, these are like primers you ordered
from IDT.
through another IDT dropship, and you have to go look up the sample code, which is like this here specific tube of IDT primer that got onboarded, and that's Y0LXEJ and so on.
Yes, that is true. And these have already been resuspended to the appropriate concentration. So.
Mm-hmm. What would happen if you tried to run this with primers that weren't resuspended? Would it know that they're
It would know
powder?
that there was no volume at all, and it will let you continue because what Emerald does is just throw you a warning saying that there is insufficient volume, but it lets you continue regardless. However, in the end, you will not have any amplification
Yes,
because
they won't
there are
work.
no primers at all.
Presumably. Yeah, fair enough. Okay.
Yeah, so you have to be mindful about. That's why I try to check the volume itself here.
Mm-hmm.
It
It will also give you a warning.
Yes, it will definitely give you a warning that there is insufficient amount of volume. So.
Okay.
Yeah. Again, I'm just kind of specifying where my samples are because since this protocol is different from the one that we already created, we have to kind of again specify what wells in which plate they are in order to kind of let the experiment know where exactly we are trying to do any operation or any modification.
Mm-hmm.
We label the plate. That's the Golden Gate reaction plate from our previous experiment, and then we are transferring the master mix into the reaction wells that I set up here. Instead of writing it all out here, I'm just specifying it as like a variable so we can just reference it directly in here.
Mm-hmm.
Then I'm adding about 40 microliters of the master mix. There's a 30 microliter of reaction itself. That is 70 total, and then I'm adding 4 microliters each of the primers, primer 1 and then primer 2, to the reaction wells.
Mm-hmm.
And this is like the PCR preparation protocol, so we are just basically adding all the different components on the PCR plate.
Yep.
Following that, I'm setting up another experiment where I'm labeling the plate and then I'm actually centrifuging the whole thing down again just to make sure everything again at the bottom of the well before we perform the PCR reaction.
Mm-hmm.
And for the PCR reaction, I'm giving it the plate itself, and then the sample volume is total of 78 microliters, reaction volume of 78 microliters. Then here are some of the PCR parameters that you would have to modify for your own use case. Activation temperature, activation time, denaturation temperature, denaturation time, primer annealing temperature, and then primer annealing time. This is highly dependent on the melting temperature of your primers, and so on, and then the extension time. So it's the regular parameters that you specify for a PCR protocol that is run on a thermocycler.
Yep.
After the PCR reaction is done, I'm letting it cool down for 30 more minutes and then centrifuging it again just to make sure everything is again at the bottom of the well.
Yep.
So what we have learned so far is like after every single step, make sure things are at the bottom of the well by centrifuging it. If not, then you might just end up with samples stuck on the side of the well, and then later on, subsequently, there might be unsuccessful transfers happening.
And something to think about. So, remind me quite how this works. Sometimes centrifuging is really easy because the centrifuge instrument is physically on the same instrument that the pipetting is happening on.
Yes.
And other times, if you add a centrifuge step, it'll cause your protocol to take like way longer to run because an operator needs to like move it somewhere totally different.
That's true.
And so this is all happening, I think, on the Hamilton, right?
Yes.
And it's in 96 well plates, and the Hamiltons all have the integrated plate
Yes,
spinners,
there is
right?
an integrated plate centrifuge on the Hamiltons that you can use.
But crucially, if you were to be doing this not in a 96 well plate, but in like an Eppendorf tube,
Right.
it would compile totally differently.
Right.
Like exactly the same command would be totally different in its physical execution in the lab if it was in a different type of plastic.
Right.
Because they would have to take it to a totally different instrument to centrifuge it.
However,
Yeah.
for this particular protocol, the PCR thermocycler itself is not integrated on the Hamilton, so they have to manually move it to the thermocycler.
So they have to take it and bring it back.
Yeah,
Okay,
they
yeah.
have to take it to the thermocycler and bring it back for the cycling, for the thermocycling, the temperature cycling that we're going to do to amplify the DNA using PCR. So,
Mhm.
yeah, and that's a really good point. Like, yeah, if you have like a Eppendorf tube or like a Falcon tube, and you want to centrifuge it in the middle of like a robotic sample preparation protocol, yes, it will take much longer because they'll have to move it to a centrifuge that is compatible for that bigger container.
And I think the Eppendorf tubes also, they have to be manually loaded into the centrifuge. It's not like
There is no automatic.
10 things down in plates, I
Right.
think is.
Yeah, doing that plates
Advice.
down in like a 96 well plate or like a 96 well PCR plate, it's always going to be like much easier and faster.
Yep.
Especially for like high throughput operations. Finally, once I'm done with this PCR protocol, I'm just trying to get what samples are coming out of this protocol. And then I'm assigning that, I'm just checking if all of them are in the same plate. So just looking at the IDs, it's a double check just to make sure like everything is in the exact plate that we are actually starting off from. So.
Yeah.
Then I'm setting up a gel electrophoresis protocol with gel input samples from the PCR protocol itself. And then I'm doing an analytical run with 1% agarose gel, sample volume of 4 microliters, a loading dye volume of 3 microliters. So the way loading dyes work is like you specify the number of loading dyes you want to actually add to your sample prep. So you are adding your original sample, loading dyes, and like a dilution buffer. So all of these three things get like mixed together and ran on an analytical gel. And the loading dyes themselves have some standards. So for example, the dyes I'm choosing here have like a 300 base pair and a 2000 base pair standard. Because the reason I'm choosing them is because I know that my construct is going to be around 1000 base pairs. So it's going to be in between those two so I can visualize them better on like a gel.
And remind me, didn't you have an iteration of this where somehow something failed because you didn't load the right loading die?
Yes. So when I actually did not like specify the loading die myself, it chose a default die which was like 1000 base pair itself, and my sample was
Right, so it's
1000
just the
base pair
wrong
too.
length.
So it kind of overlapped with my sample, and that kind of resulted in like not a really good result.
And hold on, in this gel electrophoresis protocol, and maybe you'll show me this more in Command Builder, but it doesn't seem to specify like a runtime.
No.
Is it just automatically choosing that, or how does that?
It's calculated automatically based on the percentage of the gel and the dyes you're using.
Got it. Okay.
Yes, and that is why it is important to specify the loading dyes and the appropriate size of the loading dyes you're trying to you'll be using for analysis. So in order to know what different dyes you have available for ECL, I can do like a quick search. Search model sample. So I'm just searching for any model sample that has dyed loading buffer for agarose gel electrophoresis in its name. Is what I'm trying to do here. So as you can see, there are a bunch of standard dyes that ECL offers, starting from 25 base pair all the way up to 20,000 base pair.
Cool.
And depending on your application, you can choose 2 or more of these dyes.
Cool.
So once the agarose gel electrophoresis is complete, you can actually plot the data. You can see this is the 300 base pair standard, and the other one is the 2000 base pair standard, and my sample is in between that, around 1000 base pair. And you can also visualize how the gel was run. This is a live picture that has been taken during the gel run time.
Cool.
So yeah, so
And
it is run until completion. So
the graph above is a digitization of this, right?
yes, it's just a fluorescence reading digitization of that. Yes, and they have
Yeah.
calculated these values based on the loading dyes themselves. So these values, the x-axis base pairs are calculated based on the loading dye size, and the ladder that is run along with the gel.
And this gel electrophoresis, doesn't it have the ability to do gel extractions also? Because you can
Yes.
basically fractionate. It's fractionating, so you can take a fraction
Right.
based on whichever one you desire.
Right. So the gel extraction, you would have to, instead of analytical, you'll have to perform like a preparative gel in order to
Okay.
do gel extraction. So now let's look at like how Command Center will help you build out a command from scratch. So let's look at agarose gel electrophoresis, the recently seen experiment in our script. So
So for context, so Wasim like knows how to program in this language, so you just write things straight up.
Right.
Just type brain to code. For folks who are less familiar with what the experimental options are, haven't written a command before, this tool called Command Builder is designed to help kind of show you what the options are and also compute some defaults and like suggested parameters for you based on the properties of your samples that the system knows about. So this can help you build a command, hence Command Builder. So the command as it gets built is being shown on the right-hand side, and on the left you get to set options that will appear in your command that you can then copy paste into your notebook and run.
That is true.
Basically.
Yes. And as you will see, as I choose options and like as it resolves option or like as I edit options, these will show up in the command on the right side. And you can actually copy that command over to your notebook and then run it. So it's asking me, either to specify a sample that you want to run electrophoresis on. In order to do that, I'm just going to copy one of the samples that we have here from our protocol. Then go here, then I'm going to choose select objects. Then paste it here, then choose that.
And one important thing just to know about this whole system is that here you have to specify like a physical tube that exists. Specifically, you have to specify, in order to even think about building a gel electrophoresis command, you have to have in your account a tube that makes sense to run a gel electrophoresis on. And in particular, you have to have, in this case, tube R8E1PJ and so on.
Yes.
Right. So you can't it is very difficult to assemble commands in the abstract for a general sample that might be run on a gel electrophoresis. You have to have a specific sample in mind for it to be run on.
Right. Another way, if you want to just like see how the command builder works, is like you can create a pseudo sample or like take an aliquot of water, like
exactly.
and then have that actually physical water present as a sample ID for you to actually pass on to the experiment. So,
Useful to have your favorite aliquot of water on hand to just pass to experiments so
yes,
that you can dry run them. Haha.
yeah.
Water sample. It's funny. Go ahead.
So when you select that sample, once you select, you have to click this button called Verify and Calculate. So it's going to take the sample and then calculate all the options that it needs based on that particular sample. So once you click that, it's going to do this thing.
And so this in this particular case for gel electrophoresis, I think the system does not do things like know how large the DNA polymers are in that sample and use that as a way to suggest the right ladder.
No,
right?
no,
But it could do that.
yes, it doesn't do as of now. No, it does not. Yes.
And but it does, like, the system in other scenarios that are kind of closer to chemistry, like, it does know a lot about the chemical composition of things, and it will do things like, pick the right tip size for this or whatever. Like, it will, that is the idea, is that in this step it can suggest defaults for you that actually make sense in the context of this here specific sample R8E1 that you're using.
I have actually also noticed that in some particular experiments, if your sample has like enough information, for example, like extinction coefficients, the experiment absorbance spectroscopy, for example, can decide the excitation and emission wavelengths based on your extinction coefficients. So that's pretty smart, but yeah, not in every case. So you just have to make sure things are going right way before you enqueue your experiment.
Yep.
So yeah, as you can see, it has calculated a bunch of parameters for you. These are not the only parameters. There are many more hidden. All you have to do is like click this hide null option. So there are a bunch of options that it has determined should stay as null. And if you click unclick that, it will show you all of those options too. For example, by default, it has calculated the scale to be preparative, and we do not want it to be preparative. So I'm going to click on that. And then it has chosen a default gel percentage of like 1.5. I think it should be fine, 1.5 for our purpose. And sample volume, again, it's choosing much higher because it's doing a preparative run, like a gel extraction run instead of an analytical run. And we do not have 45 microliters just to spare.
If you change it from preparative to analytic, it'll decrease its sample volume by automatically. Like if you were to unclick sample volume, change preparative, and then
I think it'll do it automatically. Yes. Yes.
Cool.
And then it also is choosing two different dyes. It's choosing the right ones in this case, 300 and 3000. So I think that's totally fine. We can also modify it if we want to, like I did in my actual experiment call where I'm using 200, 300, and like 1000 instead, 2000 instead. Sorry. Loading dye volumes, again, it's choosing higher because it's going to prepare a lot more for the sample volume itself. The sample loading volume is, again, it's related to the scale itself because it's choosing a higher volume to load onto the gel for the extraction. So let's just change the scale and see how all of these options, other options, are going to change based on our based on the preparative option itself. So once you select the option, all you have to do is click Edit option, and it'll take you to another page where you can actually edit the option. Let's change to Analytical, and then click on Verify.
And then the command on the right has updated. So all of the things that were listed over there are like default and they're like implied.
Right.
But you have the opportunity to edit them. And so basically the command you create is the list of unusual settings that you are choosing, and then everything else is like the default calculated by the system based on those that you've chosen.
A pro tip is actually to once your protocol is created, I'll show you what the pro tip is because I'll have to go back into my notebook. So once this is done, I'll show you how to look at every option that has been calculated by default. Because like in your experiment gel here, it would not show all of the options, but you can actually look at all the computed options behind the scene. Again, as you can see, if you change that, it has changed the sample volume to 10 microliters, sample loading volume to 8 microliters, dye volume to 1.3. And as
is
you
that
have
concerning?
noticed,
That's a small number.
Yes, that's why this is like way too of a small number to be loaded successfully or reliably. That is why in my previous call I have changed this volume. So I'm gonna again click on that so I can edit it later.
Got it.
Then it has calculated the separation time again, 2500 seconds automatically. Incubation fall, all of these options are kind of hidden options. Yeah, one more thing you might want to do is like not specify measure volume, because sometimes the measure volume on their the ultrasonic measure volume that the ECL has, it's not very reliable for lower volumes, especially less than 100 microliters. So you might get unreliable results from this. So I usually specify it as false, and also not measure weighted so as to reduce the overall experimentation time. Image sample sometimes can be useful for you to actually look at the sample itself sometimes for later troubleshooting. So I keep that as true.
And if you leave measure volume as true, which is default, and it does one of these ultrasonic pings and it gets a bad number, it does it that number does update the like
Yes.
volume in, and then that can cause problems if it's wrong, because then you'll get weird errors being thrown that you don't have enough sample, even though actually what was wrong was that
Right.
ultrasonic's ping was just like incorrect its reading.
Right.
And you do have enough sample.
Exactly.
Yeah.
So, okay, so I'm gonna change the loading die volume and those two options. We're gonna go to edit options. Then it's gonna again open this another window where you'll see all of the options that you have changed. So I'm gonna specify the loading die volumes to be like at least 3 microliters each, measure weight to be false, and measure volume to be false.
Right.
And then again, verify and recalculate. As you can see, this can be a slightly tedious process to build a
And
command
hence
out
if
from
you
scratch.
if you've written these before, you kind of know what settings you want, and
Right.
you can just jump right in, and you there's nothing stopping you from just typing in the code directly.
Right. Yes. Another way to
And
actually see what options are specified or what options are present for your particular sample, all you have to do is like go to the linked documentation page in our paper, and then you will be greeted onto this documentation page where you can actually uncheck this experiment option, and it will show you all of the different options that you can change and what it expects and what's the default values of those options. And
yeah,
then,
so all of Emerald's documentation is all just on the internet. Anyone can access it. It's all right. It's all right there.
right,
And it includes some very small code snippets as well that are farther down.
yes.
Um,
As you can see, there are some code snippets, but these are not super helpful if you're coding if you're changing a lot of options. So, but it's a good place to start if you want to see what the default values are, how Emerald actually does the calculation behind for each and every option, and then what's the pattern it's expecting for that particular parameter.
yep.
Going back to our page, yes, it has already calculated everything. Loading die volume to 3 microliters. Sample loading volume is 8 microliters, because for the analytical gel, you can load a maximum of 8 microliters onto the gel itself.
Ah, I see. Okay.
Yeah, and it's also chosen a ladder that it thinks that it will be good for this experiment, so you don't have to worry about it. And then the ladder frequency from our page, you can see the ladder was run before and after of all of the samples, so it's doing first and last. So you can even also
Like
change
left
that.
and right.
Yeah, you can also change that if you wanted to. So,
Cool.
yeah, I promised you that I was going to show you some pro tip, so I'm going to copy this experiment command.
Yeah.
And since these gel samples, I'm going to copy one of the samples that I have from earlier, and then I'm just going to give it one sample. And instead of running the agarose gel electrophoresis, I'm going to do something called agarose gel electrophoresis options. And I'm going to run it. So it's basically doing the same thing that we did on the command center, but it's going to show you a table of options here instead of having to go to the command center and clicking on all of these different options.
And builder.
Yes.
Yeah. Mm-hmm.
So it might take a couple seconds to finish. that you can see from here. It's evaluating. Yeah, these samples were run a long time ago, so in the database they have been marked as expired. So
Ah, fair enough.
yeah.
Probably true.
Okay, so you can see all of these different options that we could see on the command builder can also be seen here if you just run the options command.
Hmm.
And from here, you can actually, before finalizing the experiment itself by running the experiment agarose gel electrophoresis, you can actually view the options and make sure that you have the right options for the experiment and nothing wrong is going to happen during the execution itself.
Hmm.
Well, that's all I have for this particular script, and I
Cool.
hope I'll hope to see you guys next time in our next.
Thanks, Wasim.
Thank you.
Nice.